I'd like to start this presentation by thanking the International Magnesium Association for providing me with this opportunity to briefly discuss die forging of magnesium automotive front lower control arm project. It is an honor to be selected as the winner of the Wrought product category. This presentation is being made by Alex Duquette, Assistant General Manager at Multimatic Technical Center in Markham, Ontario, Canada. I should point out that the research has been performed over a 5-year period with major contributions from all parties shown on this slide: University of Waterloo, Canmet Materials, and Ford Motor Company. On behalf of the team, I'd also like to thank the Canadian government agencies listed at the bottom of the slide for the financial support. I want to start off by showing the overview of the project with the 7 main tasks. The groups that were primarily responsible for each task are listed. Let's start with the design task. Ford selected the production Ford Fusion cast aluminum front lower control arm as the baseline for comparison. Optimization was used extensively to maximize the mass savings while ensuring that all packaging and structural requirements were met. Forging process development was undertaken to characterize the properties for different magnesium alloys, forging temperatures, strain rates, and strain levels. Forging simulations were performed to predict the manufacturability of the design proposals and gain an understanding of the material flow, strain rates, and strain levels for various forging options. Forging dies were designed and built to enable prototype parts to be manufactured. Durability and strength predictions were confirmed via component level tests. Corrosion was investigated by looking at different coating options at both a coupon and component level. And last but not least, all of these research areas were integrated into one project with excellent communication and knowledge sharing between all parties and tasks. I'd now like to take a minute to explain who Multimatic is and why we wanted to be involved in this research. Multimatic Inc. is a privately held Canadian corporation supplying components, systems, and engineering services to the global automotive industry. Headquartered in Markham, Ontario, Multimatic has manufacturing divisions and engineering facilities in North America, Europe, Asia, and Australia. The top 2 images on the right show various components that Multimatic engineers and manufactures. The bottom image on the right shows the Ford GT Mark II, which Multimatic manufactures. So why did Multimatic want to participate in this research program? Multimatic is focused on finding the best solution to any problem. It is not restricted to utilizing a particular material or process when developing products. Steel, aluminum, and carbon fiber reinforced plastics are commonly used for structural applications, and this was an opportunity to add magnesium to the list of potential material options. Multimatic has supported the University of Waterloo Co-op program for over 30 years and has hired many graduates over that time. This was an opportunity to work closely with professors and graduate students to develop new technology and at the same time build on our relationship with the university. It enabled Multimatic to increase its knowledge of magnesium forging with the intent of utilizing it in future projects to achieve additional mass reduction in production vehicles. This project also enabled Multimatic to work with the Ford Research Group and Canmet Materials. And Multimatic was able to contribute by providing a suspension design, development, and manufacturing expertise to this project. The image on the left shows the front suspension system. The loads get applied to the lower control arm through the ball joint. Various combinations of longitudinal and lateral loads are transferred into the arm, as illustrated by Fx and Fy in the image. The magnesium design had to meet the strength, stiffness, durability, and corrosion requirements. Design optimization was used to maximize the mass reduction relative to the baseline arm. The initial step was to determine the maximum available package volume, shown on the top left. Optimization software is then used to determine where the material is most effective for the specific requirements. The resulting structure is shown on the top right. Later in the program, after parts were available, component-level testing was performed to verify the predicted results. A 37% mass reduction relative to the cast aluminum arm was achieved. One of the largest scientific contributions of this project was a characterization of the hot deformation behavior of magnesium at various temperatures and strain rates. On the left-hand side, you can see the traditional 1D simple upset forging in the well-known Gleeble type experiment, where the material response and resulting microstructure and texture are characterized in great detail to understand the deformation and recrystallization mechanisms. This information was used to optimize the process parameters, such as the temperature and strain rate. The application of this data is in closed die forging, shown on the right-hand side, where now the thermomechanical history is much more complex and spatially varying. The detailed material information was incorporated into deformed 3D forging simulation software to accurately predict the key response characteristics of the forging process. Magnesium has poor formability at room temperature because of limited active slip planes. However, at elevated temperatures, above 250 C, additional slip systems become active, enhancing formability. To achieve the complex final component geometry and having a very simple starting point, multiple steps were employed. This included bending, flattening, die forging, all done with magnesium at elevated temperature, and then machining. Process simulation was used to predict and mitigate flow behaviors that would result in forging defects. In production, the manufacturing process would be greatly improved, but that was beyond the scope of this study. Corrosion resistance is a major challenge, especially for a safety-critical component in a harsh environment. Coating technologies were developed that would be suitable for automotive suspension components. Coupon-level corrosion testing, based on SAE standards, was completed successfully. Component-level testing is ongoing. The research has demonstrated that with innovative design and optimization techniques, robust structural qualification protocols, and advanced corrosion protection, it is possible to use magnesium for a front lower control arm on a passenger vehicle. In closing, I'd like to thank you for your time and thank the research participants for their contributions.